Hey guys, welcome back to chapter 19, electrochemistry. So what we're going to do in this video is we're going to look at how we would balance a redox reaction, how we would balance an oxidation reduction reaction. So remember, a redox reaction is a reaction that causes a flow of electrons. So somebody in the chemical reaction is going to gain electrons. Somebody in the chemical reaction is going to lose electrons during that chemical reaction. And the way that we monitor that is using oxidation numbers. That's how we define gain and loss of electrons. So balancing redox reactions is likely a new skill for you. So some of the pieces of this is going to feel really awkward when you start doing it. But the more that you practice it, the better you'll get. The other thing that I have found with redox reactions and balancing them is it's easiest just to jump in and do it. So I'm going to quickly just go over the rules, general guidelines as to how to balance a redox reaction. And then we're just going to dive right into an example. So the first rule is to assign oxidation states. Excuse me. Rule 1 or Rule 2, you can play with which one you want to do first. So find your own path. So we're going to assign oxidation states or assign oxidation numbers to each of the individual atoms. And then we're going to separate the reactions into two half reactions. So we know that one of the reactions is going to be an oxidation. One of the reactions is going to be a reduction. So if we go ahead and just take those and separate them out, sometimes it's a little bit easier to see the oxidation and the reduction. And it's also something we're going to need to do for balancing. Step 3 is we're going to balance those half reactions by mass or balance the half reactions by number of elements. So the elements that we're going to balance first are hydrogens and oxygens. And if, well, this is where it gets kind of awkward. If there is not enough hydrogens or oxygens in that reaction, we're going to add water where we need oxygen or add hydrogen ions where we need hydrogen. So next thing you're going to ask me is, well, we can't just add things into a chemical reaction. That's not how this works. What we're just doing there is we're explaining what's happening in solution. So water's present, right? So if there's a chemical reaction and more oxygen is needed, it's going to utilize the water. If more hydrogen is needed, it's going to protonize that water. So we're just explaining what's going on here by adding the water and adding the hydrogen ions. So first we're going to balance each of the half reactions by mass or by the number of atoms. Fourth, we're going to balance each of the half reactions with respect to charge. So here's where we're going to make sure that one reaction is gaining electrons and the other reaction is losing electrons. Specifically, we want to make sure that we are looking at the number of electrons that are being lost or the number out of electrons that are being gained. Because the very next step is to make sure that the equal number of electrons are transferred. So I have to know that 2 electrons are lost in the oxidation and 3 electrons are gained in the reduction. So then in step 5, I would say, you know what? It's not 2 and 3. It's actually 6 and 6. So those are the 2 steps, again, that happen, that piggyback off each other, that happen together. So balance each half reaction with respect to charge, and then make equal the number of electrons on both sides of the reaction arrow. And then the last thing you're going to do is you're just going to write the 2 half reactions back together as one big reaction. And when you combine them back together as one big reaction, that will be a balanced redox reaction. So lots of steps here. I highly recommend that you have this map to help you through these problems. Okay. So here's the example. We are going to balance the following redox reaction. So aluminum solid reacts with aqueous copper to produce aqueous aluminum and solid copper. So this is an oxidation reduction reaction. So the first step here is to assign oxidation numbers or oxidation states. So the easiest ones, remember, are the free elements. So aluminum is by itself, that's a 0. Copper is by itself, that's a 0. Okay. This guy right here is a monoatomic ion. So with monoatomic ions, the oxidation number is just the charge on that ion. So this one is a +2, and this one is a +3. Okay. All right. So step 2 is to separate this into the 2 half reactions. So what we're going to do is we're going to put aluminum and aluminum in its own reaction. So I'm going to take aluminum solid is going to become aluminum with a 3+ charge, and that's going to be aqueous. It's going to be dissolved in solution. Okay. And then the other half reaction is copper that was dissolved in solution as an ion is going to become copper as a solid. So those are our 2 half reactions. And now we know the oxidation numbers. So here it goes from 0 to +3. So that's our oxidation. And here we go from +2 to 0. That's going to be our number going down. That's our reduction. Okay, so here's the 2 half reactions. All right. Step 3 is to balance each of the half reactions with respect to the number of atoms. So look, whoopsies. Looking at this first reaction, I have 1 aluminum, 1 aluminum. That's balanced. And here I have 1 copper and 1 copper. That's balanced. So nothing to do there, but we just needed to make sure. Now we want to balance each of the half reactions with respect to charge. Okay? So we know that aluminum is going from a 0 to a +3. So 0 to +3 is an oxidation. It's losing 3 electrons. So 3 electrons are getting kicked out. We need to add that into the equation. And for a reduction, so reduction is gaining electrons. So copper was a +2 charge. It gained 2 electrons and it became neutral. Okay. So when we say balance each half reaction with respect to charge, what we're saying is write in the electrons and where they're going. Are they being released as a product, or are we having to add them to the reactant side, put them where they belong in the reaction? Step 5 is to make equal the number of electrons. So looking at these half reactions, I cannot have a reaction that loses 3 electrons and this guy gains 2 electrons. That means I still have another electron that's just floating around randomly. And that's not how chemistry works, right? So the same number of electrons that get lost has to be the same number of electrons that get gained during that chemical reaction. So what we need to do is find the least common denominator between 3 and 2. The least common denominator is 6. So during this chemical reaction, we're not actually transferring 3 and 2 electrons. During this balanced chemical reaction, there's actually an exchange of 6 electrons. Okay? So what we're going to do is we're going to multiply the aluminum reaction by 2. So that's going to put a coefficient 2 in front of everything. And it's also going to be, we're also going to multiply the number of electrons by 2. So then we say it's losing 6 electrons. And the copper reaction, we're going to multiply by 3. So it's going to put a coefficient of 3 in front of everything. And then 3 times 2, that guy's going to be gaining 6 electrons. So we lose 6, we gain 6. That is a balanced redox reaction. Okay. So once we have these two balanced redox reactions, we're going to add them together in step 6. So electrons here, you can think of them as an intermediate, or the fact that we just don't typically write electrons into chemical equations. So we produce it, we consume it. So the balanced redox reaction is as follows. 2 atoms of aluminum have to react with 3 molecules of copper ions, and will produce 2 atoms or 2 aluminum ions and 3 atoms of copper. So that is your first look at balancing a chemical reaction. Okay. That was a pretty easy one. That one was pretty straightforward. So let's look at another one that is probably about as difficult as I can make it. So this will be one of the harder ones that we're going to balance, but we'll do it together. Okay. So we're going to balance the following redox reaction. So iron reacts with MnO4 to produce iron and manganese. Okay. So the first step is going to be to assign oxidation numbers. So here we see a monoatomic ion. So the oxidation on iron is going to be +2. Here we see manganese and oxygen. Manganese, you will see, is a transition metal. So we really don't know what the charge is on manganese. So in this case, we're going to use oxygen to determine the oxidation state for manganese. So if oxygen is not dictated by anybody else, it typically has an oxidation state of -2. All right, so here comes the difficult part. So it has an oxidation state of -2, and there's 4 of them. So oxygen brings a -8 to the table. This charge right here tells me that that molecule has a -1 charge. So when I add -8 plus the oxidation number for manganese, it has to equal a -1. That is not a neutral compound, so it does not equal 0. So -8 plus what would give me a -1? So the oxidation state on manganese must be 7. Okay, so this guy is a +7. All right, let's go to the product side. So over here we see iron again is a monoatomic. So in this case, it's a 3+. And here we see manganese is a monoatomic ion. It's a 2+. Okay. Now we want to separate this into 2 half reactions. So we're going to keep our irons together. We're going to keep our manganese together. So one of the half reactions is going to be Fe2+ becomes Fe3+. Is this an oxidation or is this a reduction? Yeah, it's an oxidation. It's losing a negatively charged particle. That number is going up. So this is going to be our oxidation. And then we've got manganese oxide becomes manganese, the ion. So we went from +7 manganese to +2 manganese for oxidation states. So that number went down. So that means it must be gaining electrons. So this is our reduction. All righty. The next step is balance each of the half reactions with respect to mass or with respect to number of atoms. Okay. All right. So the first one we have is Fe2 plus becomes Fe3 plus. I've got one iron, and that's balanced. Okay, nothing to do there. The other one is a bit more difficult. So the other one is manganese oxide becomes just manganese. Okay. So the first thing that we're going to balance is we're going to balance atoms other than hydrogen and oxygen. So we've got one manganese, other than oxygen, that's balanced. We're going to balance any oxygens by adding water, okay, to the side that lacks oxygen. So on our reactant side, we have 4 atoms of oxygen. So on our product side, we're going to need to add water, but is one molecule of water going to balance this? Nope. How many molecules of water will we need? If we have 4 oxygens on this side, we're going to need 4 oxygens on the other side as well. Okay? So we'll need 4 molecules of water. So we balanced manganese, we balanced our oxygen. Now we need to balance our hydrogen by adding H plus to the side that lacks hydrogen. Okay. So over here, we've got 4 times 2. So we've got 8 atoms of hydrogen. So to the reactant side, we're going to need to add 8 of these hydrogen ions. Okay. So remember that this process is not just making things up, right? That's what it feels like, I know. This process is really just observing what's actually going on, okay? So it's not that we just randomly put water in there because we needed some hydrogens and oxygens. It's that when this manganese oxide breaks down, it will produce 4 extra water molecules. And in order for the manganese oxide to break down, it needs to have available to it 8 hydrogen ions in order to break down. So we are just simply observing what it's doing. In your textbook, it'll talk about acidic solutions and basic solutions. We're going to stick with acidic solutions. So this redox reaction is happening in an acidic environment, which explains where those 8 hydrogen protons came from. So in an acidic environment, you can see that 8 protons would probably be available to it, right? Because that's we'll have a high concentration of those. Okay. All right, so that was step 3, balance each of the half reactions with respect to atoms. Now that we have them balanced with respect to atoms, now we need to balance them with respect to charge, or balance the electrons. So our first one was Fe2 plus becomes Fe3 plus. So we've already established that here, this is our oxidation. So lose electrons, oxidized. So losing electrons is kind of the same thing as saying that 1 electron is being produced. It's just floating away. Okay. For the other one, of course, that one's our messy one, so it'll take a little bit more thought. We've got manganese oxide plus 8 hydrogen ions. We'll produce manganese with a 2 plus 4 molecules of water. Okay. So here we're going to focus on the manganese when we focus on the transfer of electrons. So remember, manganese was a 7 plus and a 2 plus. So going from 7 to 2, that's a reduction, it's being reduced. So reduction, gain, electrons reduced. So it needs electrons in order for this to happen, right? So the electrons are going to go on the reactant side. And to go from +7 to +2, we need 5 electrons to make that change, right? So 7 add 5 negatively charged particles. Now we're down to a +2. Okay. And then lastly, we're going to balance or make equal the number of electrons. So we can't have iron losing 1 electron and manganese taking on 5 electrons. Where do those other 4 electrons come from? So in order for these two to transfer the same number of electrons, we're going to have to multiply the first reaction by 5. Okay, so we need iron to give up 5 electrons so that manganese can take on those 5 electrons. So we're going to have 5 Fe2 plus, 5 Fe3 plus, and 5 electrons. And down here we're going to have manganese oxide plus 8 protons plus 5 electrons. Manganese ion, 4 molecules of water. Okay. So again, you can think of the electrons as intermediates, or think about the fact that we don't typically write electrons into chemical equations. So now I'm just going to keep everything on the reactant side of the arrow and just add it all together. So I've got 5 Fe from the first reaction plus manganese oxide and 8 protons from the second reaction. And on the product side, I've got 5 iron ions, a manganese ion, and 4 water molecules. So that is the balanced redox equation for this example. Clear this all out so you can see this in a prettier format. And then, as always, check your work because it's easy to make little mistakes. So the best way to check your work is just to tally what you have on each side. So we start with 5 iron, we end with 5 iron. We start with 1 manganese, we end with 1 manganese. 4 oxygen, 8 hydrogen, and then you can look at the charges and make sure those are balanced as well. So again, here's just your list of rules or your map. Whoopsies. Your map to get you through these balancing of redox reactions. And as always, practice, practice, practice. And that's how you're going to get good at these. I hope you guys found this helpful.